I was asked to come and talk tonight about radiation and radiation heating. And it's a lot more complex than most people would expect it to be. Mm-hmm. And so what I'm going to do is I'm going to go to the radiation part of it first, and we'll go through that, and then if I've got time I can go back and talk about some of the other things. So if you want to just flip through that, just keep going there. Yeah, this is what I want to, what I want to start on first. And radiation factors that must be known and understood. And I was over in Europe in 1978, and that was my first exposure to radiant floor heating. And over the years I wound up going into the business and so on, and I've been at it since about 1980. And I have no formal postgraduate education, so matter of fact, my trade is a machinist, and so it's not in any way related to the academic side of it. But anyway, radiation, these are things that we should understand about radiation. It travels in a straight line at the speed of light, so it's 186,000 miles per second. And it goes in a straight line. Radiation can be reflected, and there's a great deal of controversy about some of these things because there's a lot of the authorities that have had a great deal of argument with the whole concept of radiation heating. And that's one of the reasons why I wanted to be sure I went through this. So the basis of what I'm talking about now, I will go on further to further explanation. Radiation does not heat air. And most people in North America can't understand that. But it's a fact. It doesn't heat air. And if we go on a little further, we'll talk about controls for radiation systems. Thermostats is not one of them. Radiation transfers energy from one thermal mass object to another, and at a rate that is determined by the absorption ability of the other object. Like if you're very cold and you walk into a house that has radiant floor heating, you swear you walked in under a heat lamp, because you start absorbing that energy very, very quickly. Radiation has a minimal heat loss to infiltration. You know, we tend to build these absolute airtight houses. The tighter we can get them, the better. And it's interesting, in the Scandinavian countries, they design their houses with leakage factor. The only way you can maintain a healthy thermal envelope is by having cold, dry air being drawn into the house. And they design for a 10% leakage factor. That's part of the design, and that's in Finland. I have the building codes from Finland. And log buildings, and I could talk here for an hour about log buildings alone, but in any event, I at one point was trying to use log buildings for northern housing, and they didn't have high enough R factor. And I said, well, I don't care what the R factor is. I said, I can prove to you that a log building will consume less energy than an R20 wall will, cold wall. And we ran a project up at Christopher Lake where we had 4 buildings, and one was an R20 and the other 3 were log buildings. At the end of 3 years, every log building was more thermally efficient than the R20 was. I'm going to talk about this later, but no, that's okay. Oh yeah, radiation transfer creates an inverse stratified thermal gradient. If you have a radiant floor heating system, it's cooler at the ceiling than it is at the floor. That makes a huge difference in terms of energy loss or transfer. Radiation delivery systems reduces energy input by a minimum of 30%. And in our climate, I think it's more like 40%. We've done, well, between design, supply, install, we've done about 4,000 systems now in North America. Now most of those were designed, but about 2,500 of them that we actually built. And there's any combination of supply, install, design. Thermostats cannot properly control radiant floor heating. And radiation heating, when it was introduced to North America, everybody in North America, of course, was forced air. And every forced air system is controlled with a thermostat. And the unfortunate part of what happened in North America is that they tried to control radiation heating the same way as they controlled forced air. I'm not saying it doesn't work. It doesn't work as well as it should, though. Yeah, radiation is best controlled by the state of flux. In other words, the differential. And we'll talk about that a bit more in the next slide here. Yeah, you often hear people talk about how you can't transfer heat through a vacuum. Well, solar radiation comes through 93 million miles of vacuum at a minus 270 degrees C temperature, and there's still 440 BTUs per square foot reaches the Earth's outer atmosphere. And it again travels at the speed of light. Next one. In any design that we do nowadays, the first and most important thing, this is getting off radiation, but the most important part of our whole design is the thermal envelope. And thermal envelopes can be far better than anything that we have done in the past. We've got thermal envelopes down to 5 BTUs per square foot. And that's not that difficult to do. Anyway, this is as far as we're concerned, this is our priorities. So the first thing we look at is the thermal envelope. Then we assess energy sources, as many natural sources as we can find. And then the energy distribution system, which of course we use radiation, and then the mechanical heating system. And that's the least we can use combustion systems, etc., the better. That's the way we assess it anyway. We're missing something there.
Back up?
Yeah. Maybe back one more. One more. Yeah, this is the part that I had missed. Radiation is self-compensating. Radiation heating systems are self-compensating. The absorption rates increase as temperatures fall and decrease as temperature rises. So the whole concept of radiation heating is to try to maintain as many constants as possible. And as soon as it gets colder or cooler, I mean, the radiation emits faster at a higher rate, and vice versa, going the other way. Radiation is best served by constants. Like if you can run constant flows with variable temperatures, or constant temperatures with variable flows, is the best way to run radiant heating systems. And it sounds complex, but it isn't particularly. Bruce is doing it all the time. And one of the problems that you've had with radiation heating systems in North America, because everyone has tried to use a forced air control system to run radiation, and as soon as you do that, as soon as you close off a flow in a loop, it increases the flow everywhere else. Or if you close off a flow, then one area gets cold quicker, And then when it opens again, it gives a surge of colder water back to the boiler, which means that the boiler is confused, doesn't know what's going on. So the way we do systems is we run constant flow, and we use outdoor reset controls, and we adjust the control to meet a constant demand, or in other words, create a constant temperature in the most critical zone in the envelope. Like if this room was the most critical zone, you'd adjust the outdoor reset control until you have a temperature that is consistent. Doesn't matter if it's minus 40 outside or 0. The temperature stays the same. There's also a capacity for shift in that, for hotter or colder. But by doing that, you use the one zone control for this zone, and you adjust this temperature until you meet this, until you get this constant demand, constant supply. And then all the other zones, all the rest of the zones in the building, you adjust with flow by reducing the flow rate. So once you've met the demand in the most critical zone, everything else can be adjusted by reducing the flow rate. And when that's all set up, and it isn't as difficult as it sounds, I mean, plumbers tend to hate it because they want to put a thermostat on the wall and be gone, you know. And there is a bit more to it, to do it this way. But we've done enough of them that we can usually leave a job site and maybe have one callback, that's about all. When I talked about the thermostats and zone valves create erratic flows, if you're using thermostats and zone valves, you should be using a load flow ratio pump. And these pumps have just come available here in the last year or so, like Grundfos and Willow. They've been out in Europe for years and years and years, and that was the reason that they used them, is because when you shut off a flow, it didn't increase the flows everywhere else. It was to maintain consistent flow rates. Outdoor sensors should be used to establish operating temperatures. The outdoor temperature is what determines the loss of any envelope. So if you use the outdoor temperature as the thermostat, it establishes an operating temperature for the system, and then then of course you go through a control process like I was talking about before, just before this. But you again have a supplied temperature, and then that adjusts to suit the loss of the envelope. Indoor sensors are really good in terms of adding another dimension to the control capacity, because an indoor sensor, while we do lots of systems without indoor sensors, but an indoor sensor does have to leave the knowledge based on the comfort level. In other words, the temperature. While I'm saying the temperature is not the ultimate control, as a matter of fact, it's not a very good control system at all. But the indoor sensor does add another dimension to the control process. And there's some other theories too related to radiation heating. We haven't researched it or prototyped anything, but there's one theory that says if you maintain a constant temperature in the floor, in other words, the floor is always the same temperature, and you control it by, and this is the state of flux that I talked about earlier, you control it by the return temperature. So you want to maintain this state of flux so that you're delivering whatever load factor is required. The temperature changes based on outdoor temperature. So it's the outdoor sensor that determines the operating temperature, and then you got to maintain a certain temperature differential based on the load factor. Another theory that's one measures the return temperature to determine state of flux, and the other one just has a floor sensor. I think the return temperature